Hello everyone and welcome back. We are doing queuing theory. We are done with the basics that are required in queuing theory. We are done with understanding what a queue is, why is it formed, where is it formed, service stations, length of a queue and so on. We are now entering into the four very important aspects that we are trying to study in a queue, and that is number one, length of a queue, and this is denoted by LQ. Number two, length of a system, and that is designated by LS. Number three, waiting time in a queue, that is WQ. And number four, waiting time in a system, and that is WS. Along with these four things, there is another thing that I am going to, or we are going to have to do, and that is number five, probabilities. What do you mean by probabilities? There are certain number of people that are coming in every hour. Do you guarantee that only those many people will come? No, it's random, sometimes more, sometimes less. So what are the chances that right now in my system there are 5 people? What are the chances that right now in my system there are 10 people? And that is given by Pn, also known as probabilities of n people in the system. Probability that there are n people in the system is given by the notification Pn. And all this will be found with the help of one and only one thing, and that is rho, also known as your utilization factor. So how well are you utilized will tell you what the length of the queue is, what the length of the system is, what the weighting of in the queue is, what the weighting in the system is. Rho is given by lambda by mu and is always less than 1. First, let me focus on these, and I'm telling you, pay attention, listen to whatever I'm saying, because the institute material has done this in a different way. If you try to remember those formulas, you will pull your hair out and lose your mind. So pay attention to whatever I'm saying. The one thing that we are going to do, no matter what they ask you, and these are the only 4 things that can ask. No matter what they ask you, you will find one and only one thing first, and that is length of the queue. The length of the queue is given by the formula rho square upon 1 minus rho. I am going to do formulas only and only with the help of rho. They have done formulas with lambda and mu, which becomes very difficult to keep a tab of. So, length of the queue is given by rho square upon 1 minus rho. Then what is length of the system? The length of the system is length of the queue plus the people getting served. Now let's go back. You will say, sir, here length of the queue is 1, 2, 3, 4, 5, and the people getting served is 3 people getting served. So it is 5 plus 3. Well, that's wrong. And listen to what I am saying carefully. See, this is a statistical approach. It's not exact values. This is your server, and there is a person sitting here, and in the queue there are 3 more people. Question: What is length of the system? 3. Sorry, what is length of the queue? 3. 3 people in the system. What is length of the system? Well, length of the system is 4. 3 in the queue and 1 person getting served? That's wrong. Listen to what I am saying carefully now. If I am serving at a rate of 75%, if the value of rho is 0.75, which is I am servicing 75%. Now whatever I am going to say is going to sound very vague, but try to understand it at your level. This person sitting on the server, has he gotten served? He is getting served. So he is in the process. Okay. If he is in the process, or imagine this. Suppose I have a 10-minute job on the system, out of which 5 minutes are done. So can I say I am only half served and there is still half that is yet to be served? So can I say that half part of me is still standing behind in the queue? I'll repeat this. It takes 10 minutes for me for service. I am done with 5. So 50% of the service is done. Or I have 100 things to do on this server. 50 things are done. Then can I say 50 things are pending? If 50 things are pending, aren't these 50 things still standing in the queue behind? Yes, there are. So if your service rate is 75%, you are served only 75%. There is still a 25% part of you that is still in queue. So if you ask me how many people in a queue, it is 1, 2, 3 and 25% of this person who is still not served. So the answer is 3.25 people in the queue. And how many in the system? Well, 3.25 in the queue, and the 75% that is being served is 3.25 plus 0.75, which is a total of 4. So there are 4 people in the system, but the split is one entire person is not served. Only 75% of that person is served. If the same example I give you with 2 servers. So one person sitting here, one person sitting here, and 3 people still in queue. Length of the queue 3. Well, 4 now correct. Length of the system 3, 4, 5. Well, that's wrong. Why? I'll tell you. Here no, when you are saying that one person is being served, that's wrong. My efficiency is 75%, so only 0.75 part of the person is served. And here also only 0.75% part of the person is served. There is still a 0.25 from here that is not served. There is still a 0.25 from here that is not served, which means both together is 0.5 that is still not served, and 7.75 plus 7.75, which is 1.5 that is served. So it's not 3 plus 2, 5. It is 3.5 plus 1.5, which is 5. I know it's a little difficult to understand, but try and humor me. Like I said, nobody's going to ask you the real meaning of it. If you understand that, I will tell you this. Length of the system is the length of the queue plus the part of the person that is taking service. How much part of the person is always taking service? Well, rho is my utilization, and that part of the person is taking service. So LQ is rho square upon 1 minus rho. Length of the queue, length of the system is length of the queue plus the part that is being served. And then the rest of the two are very, very easy. LS is given by lambda WS and LQ is given by lambda WQ. That's it. If you remember this, it's gold. You don't have to remember anything that they have written, and you can solve any question that they ask. No matter what they ask you, the first thing you will find is rho. How? Lambda upon V. Once you found rho, length of the queue is rho square upon 1 minus rho. This is the only formula I want you to remember. Length of the system is length of the queue plus rho. Length of the system is lambda WS. Length of the queue is lambda WQ. I know here we are going to find WS and WQ. That's okay, but we'll use the reverse pattern. And a few other things that I said that they might ask you is, what is the probability of nobody in the system? Well, simple. What does rho tell you? How well I am utilized. So in the previous question, remember, you are 75% utilized, which means 25% you are idle. You tell me, when is somebody idle? Simple. Somebody is idle when there is nobody there to take service. If there is nobody to take service, the server is going to be idle. Then the probability that there is nobody in the system is 1 minus the utilization. Because if the utilization is 75%, 1 minus 0.75 is 0.25, which means 75% you are utilized, 25% you are idle. If you are idle, it means that there is nobody in the system. So probability of nobody in the system is 1 minus rho. And then the last, probability of n people in the system. Now don't get confused between my rho and my p. This is probability of 0 people in the system, probability of n people in the system, and this is rho. Probability that there will be n people in the system is rho raised to n p 0. That's it. If these 6 formulas, there are 1 or 2 more, but that I will explain when I do questions. If these 6 formulas are in place, and that too you don't need to, I don't think you need to by heart them. We'll start with length of the queue. Length of the queue is rho square upon 1 minus rho. Length of the system is length of the queue plus the part being served, which is rho. Length of the system is lambda WS. Length of the queue is lambda WQ, and a probability of nobody in the system is 1 minus rho, and probability of n people in the system is rho raised to np 0. If you have this in place, all questions can be solved. Let's come to the first question that we are going to, and this is what is important. If you've understood whatever I have extra that I've told you, fantastic. But if that is too cumbersome, it's okay. I just want you to understand the concept and where things come from. Once that is done, this is what is going to be asked in every question. This is my arrival rate, this is my service rate. Can you tell me at a given point how many people will be there in the system? How many people will be there in the queue? What if a person walks in? How long will the person have to wait in the queue? How long will the person have to wait in the system? What are the chances that at a given time there are 10 people in the system? What are the chances that there are at a given time there is nobody in the system? Are the questions that are going to be asked. Let's come to the questions from your institute material, queuing theory. Question number 1 says, question number 1 for me in your institute material, it is page 89, question number 7. Customers arrive at a bakery at a rate of 16 per hour. So the arrival rate is 16 people per hour. The arrival is described to be Poisson distributed. So the arrival is random, but we've tried to generate some kind of a heterogeneity from the randomness. And we've realized that on an average, 16 people come to the bakery. Each clerk can serve a customer in an average of 3 minutes. Now, do you notice that arrival is given to you as a number, which is 16 per hour. But service is not given to you as a number. Service is given to you as a service time. Remember I told you that is why service is exponentially distributed, because time is exponential. This time can be described as an exponential distribution with a mean of 3 minutes. So what do I have to do? I have told you one thing. I can't deal with time. You tell me how many people come in an hour and how many people take service. If you haven't told me, I will convert it. So you've told me how many people come. You haven't told me how many people get served. But you told me that on an average, I give service in 3 minutes. Well, if you give service in 3 minutes, every 3 minutes, I serve one person. So if every 3 minutes you serve one person, then I will find out how many people do you serve in 1 hour. What do you want from me? Question number 1. What is the arrival and service rates? Okay. Compute the average number of customers being served at any time. Or let's do one thing, no? See, any question they will ask you these 4. Apart from these 4 things, they might ask you probabilities. But see, for me, no, this flow is very important. No matter what they ask me, I will always find LQ, LS, lambda Q, WS, WQ. That's it. So let me do one thing, no. Let them ask whatever they want to. I will answer you only in this pattern. So let's do one thing first. Let's first find what we can and then give them answers for whatever they want. Let me get rid of the question. So let me write down the data. And the data is arrival you have directly given me as a number. So fantastic. You are saying that customers arrive at a bakery at an average of 16 per hour. So arrival rate is 16 per hour. So lambda is 16. The arrival can be described to be Poisson distributed with a mean of 16, which is correct. Each clerk can serve a customer in an average of 3 minutes. So time required for service is 3 minutes. So for people who understand, 60 divided by 3 is your answer. But for people who don't, basic. One person gets served in 3 minutes. I want to know in 1 hour. So X persons get served in 60 minutes. Cross multiply. X is 60 by 3, 20. Or you can say mu persons get saved. So mu is 20. So people arrive at the rate of 16. So 16 people come to my bakery in 1 hour. But I have the capability of serving 20. Good enough. Lambda is less than mu, and that is my main objective. If lambda becomes more than mu, do something, first change that, then start studying your system. So I have mu, which is service rate 20 per hour. So I have lambda is 16 and mu is 20. Once you found lambda and mu, your next job is to find rho. Rho is lambda upon mu, which is 16 upon 20. Now it's up to you what you want to do. Rho is always a value less than 1. So it will always be a decimal value. It's up to you how you want to look at it. Some people like keeping it fractions. Some people like turning it to decimals. I have a different approach every time. My approach is that, see, if the denominator divides the numerator perfectly, then divide. Because 16 by 20 is a perfect value. 20 is not a troublesome number. 0.8, which is not a problem. But if suppose this was 30, then 16 divided by 30 becomes like a very weird recurring decimal. Then I don't prefer cancelling it completely. I prefer keeping it in fractions. So I have the value of rho. Once I have the value of rho, I can find anything that the 4 lists that I can. Length of this queue. So in this system, at a given, anytime, if this shop is open for 8 hours, anytime I go, how many people will I see in a queue? Well, the average length of a queue will be rho square upon 1 minus rho, which is 0.8 square upon 1 minus 0.8. 0.8 square, now you can finish it off in the calculator. No problem. I am writing it as 0.8 into 0.8 divided by 0.2. So one decimal shift, this becomes 4. 8 4s are 32. 3.2 is my answer. So every time you go to this kind of a shop, there will always be 3.2 people in the queue. Now you need to understand, how can there be decimal people in the queue? Even I agree with you. Can't be decimal people in the queue. But this is averages. This is how averages work. On an average, there are 3.2 people in the system. And then once I'm done with this, I will show you something very beautiful, how everything just adds up. If I ask you length of the system, well, it's basically whatever the queue length is plus that person or that part of the person that is being served. So length of the queue is 3.2 plus the part of the person that is served is 80%, which is 0.8, which is 4. Perfect, no? 4 people in the system, out of which 0.8 part of the person is being served, which means 3.2 is still in the queue, or the 0.2 part is in the queue. So technically when you see it, how will you see it? You will see 3 people in the queue and 1 person on the server. But that 1 person is not 100% served yet. He is only 80% served. 20% of the person is yet to be served. So theoretically that 20% is still standing in line. Uski आधी आत्मा line में. Let's come to the next. Length of the system is lambda ws. Length of the system is 4. Lambda is 16. Waiting in the system. So 16 goes on the other side and divides. Ws is, I'm writing this directly, I hope you understand, 4 divided by 16. What is 4 divided by 16? 4 divided by 16 is 0.25. So this is 0.25, and I've always told you that waiting time is time. So it is, Ws is 0.25 hours. But can I say 0.25 hours is 0.25 into 60 minutes? What is 0.25 hours? It's quarter of an hour. What is quarter of an hour? 15 minutes. So 0.25 into 60. The answer is 15. 15 minutes. And now LQ is lambda WQ. Length of the queue is 3.2, is lambda, which is 16, into WQ, or WQ is 16 divided by 3.2. 16 divided by, 16 will come on to the other side. 3.2 divided by 16, and the answer is 0.2 hours. 0.2 hours is 0.2 into 60 minutes, which is 12 minutes. And look at something, how beautifully it adds up. You are in the system. So if you go to you go to the bakery, you are in the bakery for a total of 15 minutes. Out of the 15 minutes, 12 minutes you were standing in line. What about the rest of the 3 minutes? Rest of the 3 minutes I was getting service, no? The total of 15 minutes. That's your answer. So at any given point, if you enter this bakery, you will always see 3.2 people in the line, total 4 people in the system. So you understand how this becomes 4. So that person, there is one person standing at the counter. The clerk is helping. But that person's only 80% needs are met. 20% needs are not met. So that 20% we consider still in the queue. We don't consider served. So we consider only 80% served. So 4 people, technically 3 in the queue and 1 getting served. But we say 3.2 in the queue and 0.8 getting served. A person who comes to this bakery spends an entire 15 minutes in the bakery, out of which 12 minutes are spent in the queue, and obviously 3 minutes you told me, you give service. 3 minutes are sent for service. It's a very beautiful concept, management concept. Unfortunately, it's very weirdly put in a lot of concepts, all the concepts rather, very weirdly put in your institute material. Anyway, let's look at what they want and what they have written. So, Again, remember my way of writing down formulas, because I told you theirs is very weird. To begin with, what is the average arrival and service rate? So this is the answer. The arrival is, where did it go? 16 per hour. And the service rate is 20 per hour. And then they've written all of this, which is what I have written, but they have written in a different way. Whatever it is, the bottom line is, what is the arrival and the service rate? The arrival rate is 16 per hour and the service rate is 20 per hour. Done. Question number 2. Compute the average number of customers being served at any time. Compute the average number of customers being served. Then can I say, I'm asking you, how well are you utilized, or what part of a person is getting service? Well, 0.8, which is 80% part of the person is getting service, which means that B, the average number of customer being served at any time is rho. They've written it as R because they didn't want to type rho, so they've written it as R, which is 0.80, and that is the customer being served at any time. Now after this they've written all this, and that is why I told you all their formulas are in terms of lambda and mu. Don't remember it that way, you'll go crazy. Remember the formulas like I have given you the formulas. Let's come to C. Suppose it has been determined that the average number of customers waiting in line is 3.2. Why have you given me this data? Are you stupid? Can't I find the average number of customers waiting in the queue? And I did. Didn't we find the average number of customers waiting in the queue? Yes, we did. We did find the average number of customers waiting in the queue, and the answer is 3.2. Why did you have to separately give it to me? I could find it. But that's okay. Now they've given it. We've also found it. Tallies, whatever. Let's go back. Suppose it was determined that the average number of customers waiting in line is 3.2. Compute the average number of customers in the system. Well, I did. The average number of customers in the system is 4. 3.2 in the queue and 0.8 being served. Let's look at their solution. Here. So they've written LS is LQ plus rho, which is 3.2 plus 0.8, which is 0.4. Now the rest, why have they found? They only know, because not asked. Or did I not read? Yes, they have asked. Compute the average number of customers in the system, that is waiting in line to be served. Waiting in line or being served. So the entire system. The average time a customer waits in line and the average time in the system. Average time customer waits in line is WQ and average time in the system is WS. WQ according to me is 12 minutes. Yes, mine is also 12 minutes. Waiting in the system according to them is 15 minutes, which is also correct. So 15 and 12, which is also correct. Let's come to the last part. Determine the system utilization for M is equal to 1, 2, 3. Now, remember, according to my model, I had written that number of servers is C. They write number of servers is M. So make that change. In the place of my C, you will have M. So if you are increasing the number of servers, one clerk can serve 20 people. If you put 2 clerks, it will increase the service rate, and 2 clerks together can serve 40 people. 3 clerks, well, 3 clerks together can serve 60 people. So if you want to know the utilization with 1 server, 2 servers and 3 servers, I'll tell you what the utilization will be. Utilization, which is rho, is basically lambda upon mu, but this is if there is 1 server. If the number of servers increase, we multiply that by m. So, since lambda is 16 and mu is 20, with m equal to 1, rho will be 16 upon 20 into 1, which is 0.8, is my utilization. When m is equal to 2, rho will be 16 upon 20 into 2, which is 16 upon 40. What is 16 divided by 40? 16 divided by 40 is 0.4. And lastly, when m is equal to 3, rho is 16 upon 20 into 3. Rho is 20 into 3 is 60. So it is 16 divided by 60, and the answer is 0.266666. You can write it as 0.27. That's it. Let's check what their solution is. Well, here with one server 0.8 80%, with two servers 0.4 40%, with three servers 0.27, which is 27%. You obviously, if you increase the number of servers, your utilization is going to decrease, because you can as it is serve more people than that can come. So imagine if like in this case the number of people entering the system is only 16, but you can serve 40 people. So imagine 16 people come in, you can serve 40. So you will serve the 16 people, and the rest of the time you will sit idle. So your utilization will decrease. Length of the queue. When there are three servers, you can serve 60 people. 16 people come every hour, but you can serve 60 people. So you will be very little utilized. That's it. And that is all that they are expecting from this question. That is question 1 in queuing theory. Let's come to the next question, which is question number 3. You find whatever, next question, which is question number 2. You find whatever you can and then answer whatever questions they are asking. An airline is planning to open a satellite ticket desk. So what is it? It's nothing else. It's a server where people will log in and buy an airline ticket. So it's basically an online ticket, but they call it a satellite ticketing desk. Okay. In a new shopping plaza. So it's basically going to be like a kiosk machine where you go, it's self-help. You press the buttons. This machine is dedicatedly only going to work for booking tickets for this particular airline. Staffed by one ticketing agent. So there is one ticketing agent, which means there is a single server. It is estimated that requests for tickets and information will average at 15 per hour. So people will ask for tickets on an average of 15 per hour. So the request arrival is at the rate of 15 per hour, and the requests will be Poisson distributed. Perfect. So random but Poisson distributed. Service time is assumed to be exponentially distributed. Previous experience with similar satellite operations suggests that the mean service time should be an average of 3 minutes. Again, they have not told you how many people I can serve in an hour. They have given you the time required for service for one person. That's okay. Then I will find out then in 1 hour how many people can you serve. Now they've asked you system utilization, percentage of time a server is idle, expected number of customers waiting to be served, the average time customers will spend in the system, the probability of 0 customers in the system, and so on. Can we do one thing? First thing I'm going to do is I'm going to find rho and my 4 things and then give you whatever you want. So let's begin with our solution. An airline is planning to open a satellite ticketing desk in a new shopping plaza staffed by one ticketing agent, which means there is one and only one server. It is estimated that requests for tickets and information average at 15 per hour. Then can I say arrival is happening at the rate of 15 per hour? What about service? Well, I service one person in 3 minutes. Then again the same. One person 3 minutes. Then new people will be served in 60 minutes. Then new is 60 by 3, which is 20 per hour. So my arrival is happening at 15 per hour while my service is happening at 20 per hour. So the rho, which is my utilization, is given by lambda upon mu, which is 15 upon 20. And 20 again is a very good number, so that is why division is possible. 15 divided by 20 is 0.75, or in other words, I am 75% utilized, or my system is 75% utilized. 25% of the time, because of no arrivals, it has to be idle. That's okay. Let's start with, at any given time, how many people will be standing in a queue in this system? Or if want to talk to if this is, let's say, over a phone, if I want to talk to that ticketing agent, if I call them and then say you are waiting and you are in line, wait for some time, for how long will I have to, how many people are there total in the queue? Length of the queue is row square upon 1 minus row, which is 0.75 upon 1 minus 0.75, which is 0.75 upon 0.25, which is 75 upon 25, which is 3. There are a total of 3 people in the queue. How many people in the entire system? Sorry, I made a mistake here. It is 0.75 square, 0.75 square. So let me do one thing. Let me finish this off in the calculator. 0.75 square it and then divide it by 0.25. The answer is 2.25. I'm sorry. So the answer is 2.25 people in the queue. How many in the entire system? Well, the queue plus the person that is getting served. The queue is of 2.25 people plus the person getting served is row, which is 0.75. So which means a total of 3 people. But you get the idea. So what it means is 3 people in the system. So this is how, when you see it, you will see it like this. A total of 3 people in the system, 2 in the queue and 1 getting service, but the one that getting service is only 75% served, 25% is yet to be served. So that 25% I consider in the queue. So it is 2 plus 0.25 here, which is 2.25. LS is lambda WS. Length of the system is 3. Lambda is 15 waiting in the system, or waiting in the system is 3 by 15. What is 3 by 15? 3 divided by 15 is 0.2. 0.2R. 0.2R is 0.2 into 60 minutes, which is 12 minutes. Is the waiting in the system. LQ is lambda WQ. Length of the queue is 2.25, which is lambda, which is 15 into WQ, or WQ is 2.25 divided by 15. 2.25 divided by 15 is 0.15. 0.15 R. 0.15 R is 0.15 into 60 minutes, which is 9 minutes. And perfect, no? 12 minutes I am in the system, and you only told me that you serve at 3 minutes per person. So 12 plus 3 is, 9 minutes I am in the queue plus 3 minutes getting served is a total of 12 minutes in the system. What do you want? Let's start answering one question at a time. Question number 1. What is the system utilization? So you start writing this one at a time, declaring, giving them. So this is for you. Once you are done with this, give them one answer at a time. So write down A. System utilization is, what is your system utilization? 75%. Correct? Let's check their answer. System utilization is 0.75. Next. Percentage of time the server or the agent will be idle. Now this we haven't found, but simple. See, if the person is occupied 75% of the time, then 25% of the time he or she is idle. So probability of idle or probability of nobody in the system is 1 minus rho, which is 1 minus 0.75, which is 0.25. So 25% of the time there is nobody in the system, and that is why the system is idle. The answer to that, percentage of time the server will be idle is 25%. Question number C. The expected number of customers waiting to be served. That's a very good question. Expecting number of customers waiting to be served. So you're asking me number. which means you're either asking me LS or LQ. But which one out of the two? Expected number of customers waiting to be served. So they are not served yet, they are waiting, which means they are waiting in queue. So you are basically asking me the length of the queue. What is the length of the queue? The length of the queue according to me was 2.25. Let's see what their answer is. Expected number of customers waiting to be served is 2.25. Next, D. Average time a customer will spend in the system. So you're basically asking me the time spent in the system. So WS is what you're asking me. According to me, WS is 12 minutes. Let's see what their answer is. Their answer is WS is 0.20 hour, which is 12 minutes. Perfect. Next, D. An extra question without any naming. Probability of 0 customers in the system and probability of 4 customers in the system. Will you ask probabilities? Probability of 0 customers in the system I've already found. If you want to write it down directly, write it down again. Probability of 0 people in the system is P0, which is 1 minus rho, which is 0.25. And now if you want probability of n people in the system, it is rho raised to n P0. So probability of 4, if I am correct. Yes. Probability that there will be 4 people in the system is rho, which is 0.75 raised to 4 into P0, which is 0.25, which is 0.75 raised to 4. 2, 3, 4 multiplied by 0.25. The answer is 0.07910. 0.07910. Let's see what their answer is. Their answer is 0.07. They haven't written the 0.10, which is okay. And that is question number 2. Next question is question number 3. I want you to skip that. We'll do that later. Let's come to question number 4. A departmental store has 1 cashier during rush hour. Customers arrive at a rate of 20 per hour. So arrival is given to you, which is lambda, which is 20. The average number of customers that can be handled by the cashier is 24 per hour. See, they've given you this directly, lambda and mu directly. Assume that the conditions use a single queuing channel model. Find the average time the customer spends in the system. So nothing else asked, only one thing. Average time the customer spends in the system. Time. So it's W. In the system, so it's WS. So that's the only thing that is asked, nothing else. Fantastic. Let's start then. And everything is given. So I think in 2 or 3 lines this question will be done. And that is lambda is 20 and mu is 24. Rho is lambda upon mu, which is 20 upon 24. Now this is where my problem begins. See, when you do a 20 divided by 24 becomes a recurring decimal. I don't prefer that. So I'm keeping this in fractions. So I'm reducing it to the smallest fraction I can. So both go in 4. 4 5s are 20, 4 6 are 24. I'm keeping it this way. 5 by 6. That's it. You want waiting in the system. For waiting in the system, I need length of the system, and for length of the system, I'm going to find length of the queue. That is why I'm telling you, see, don't bother by hearting all formulas. Go in the flow and then find them whatever they have to. So I will first find the length of the queue. Length of the queue is rho square upon 1 minus rho. Now you have to be a little careful because our rho is a fraction. So it is 5 by 6 square upon 1 minus 5 by 6, which is 5 by 6 into 5 by 6 is 5 by 6 square divided by 1 minus 5 by 6 is 6 ones are 6 minus 5 is 1 by 6. Can I say one denominator can cancel? My pencil, see, here it is. So I am left with 5 5s are 25 by 6. Now you can convert this, but then again this will become a very odd decimal, and that is 25 divided by 6 is 4.16666. So 4.17 if you want to write. But length of the queue is not asked. What is asked? Waiting in the system. So I want length of the system. Length of the system is length of the queue plus row. See, length of the queue is 25 by 6. Row is 5 by 6. So that becomes 25. I can add directly because same denominator. 25 plus 5 is 30 by 6. 6 5s is 30. So the length of the system is, there are 5 people in the system, out of which 4.17 is in the queue. And then the rest, which is whatever is left, which is going to be 8.3 is getting served, and wasn't 20 by 24. 0.8333. Correct. So 83% is getting served. 17% along with the rest of the 4 are still in the queue. Anyway, I wanted WS. So I'm going to say LS is lambda WS. Length of the system, which is 5, is lambda, which is 20 into waiting in the system, which has to be found. So WS is 5 by 20. What is 5 divided by 20? Well, 5 divided by 20 is 0.25, or quarter of an hour, and quarter of an hour is nothing else but 15 minutes. So if you want waiting in the system, the answer is 15 minutes. Now see, what they could have done is, they could have directly used a WS formula, which is what they have done, if you notice. No, they have done LS. Yeah, so LS they found directly using a formula. I haven't done that. I found LQ from LQLS from LSWS. Anyway, the final answer is 15 minutes. Correct? Which is same in both cases. So our answer is perfect. That is question number 4. The next question that I want to do is, I want to skip everything in between and directly go to the last question on that sheet, which is question number 6, which according to your module is question number 93, or question number on page 93, question number 12. The question says, workers come to a tool store room to inquire about special tools. So workers are coming to a tool store room to inquire about tools. Okay. For accomplishing particular projects assigned to them. The average time between the two arrivals is 60 seconds. See, now arrival is not given to you as a number. What have they said? Every 60 seconds, one person comes for asking for service. And the arrival is assumed to be Poisson distributed. Fantastic. The average service time of a tool room attendant. So, when they go to get service, there is a person who is providing this service. I'll explain this example to you. Just let's read first. The average time the attendant takes to attend to that person is 40 seconds. You know what this is? So, ये जो बड़ी-बड़ी construction sites होती है ना, वहाँ पे every person is given a certain number of standard tools. जैसे एक हथौड़ी मिलेगी, एक screwdriver मिलेगा, वगैरह वगैरह. But there are special tools that are not given to everyone. What you do is, there is a tool room or a tool shed. You go there, and because maybe these equipments are expensive. So what you do is, you go there, you write your name down and you tell the person कि ये चाहिए. You write your name down, write there what have you taken, when have you taken, date, and sign it. And then when you come back to give it, the tool room attendant will look at it, inspect it, and then tick कि बाबा लेके गया था, अब देके भी गया है. There are a few sites or organizations that have it compulsory that if you have picked something up, you have to submit it on the same day. अगर कल वही चीज चाहिए काम करने के लिए, come back tomorrow morning, I will give it to you. But right now, I want you to make sure that you take it and give it to me today itself. So what happens is when people come to the tool shed, there are already people who are actually trying to take something. So then there are people that have formed a queue now. What are they saying? People arrive at a rate of 60 seconds. So every 60 seconds, one person comes in. So now you tell me, isn't 60 seconds basically 1 minute? So you are telling me that every 1 minute, one person comes there. Okay. So arrival is 60 seconds. I don't understand 60 seconds. I want to know in 1 hour how many people arrive. Well, simple. 1 hour is 60 minutes, which is basically 60 into 60 seconds. 6 6 are 36, which is 3600 seconds is 1 hour. So simple. 1 arrival in 60 seconds. Then lambda arrivals in 3600 seconds, which is basically 1 hour. Cross multiply, lambda is 3600 upon 60, which is, what is 3600 divided by 60? 60. So it is 60, which means, and basic common sense, every 60 seconds if one person comes, which means every minute one person is coming, which means in 1 hour 60 people will come, 1 minute per person. So the arrival is happening at a rate of 60. What about service? Well, it takes 40 seconds to serve one person. Service is at the rate of 40 seconds. I don't understand this. I don't care how much time you take to serve a person. Tell me in hours how long does it tell me in 1 hour how many people do you serve. So I'm going to say one service in 40 seconds. Therefore, mu services in, again 1 hour is 3600 seconds. Cross multiply, mu is 3600 upon 40, and that is 3600 divided by 40 is 90. So there are 90 people that are served. So arrival is happening at the rate of 60 and service is happening at the rate of 90. Is the rate of service greater than that of arrival? Yes. Then it is perfect, no problem. So I have lambda is 60 while mu is 90. Then rho is lambda upon mu, which is 60 upon 90. And again 60 and 90 will become a recurring decimal. So it's up to you what you want to do. 60 divided by 90, if you do, it is going to be 0.66666. Or what I would prefer is, I would say 32s are 33s are 2 by 3. You can write it as 0.66666, which is approximately 0.67. I am keeping it as 2 by 3. Once you have the value of rho, I can find you anything, everything. What all can I find you? Number one, LQ is rho square upon 1 minus rho. Now your rho is 2 by 3 square upon 1 minus 2 by 3. 2 by 3 square is 2 by 3 into 2 by 3 divided by. Cross multiply, 3 minus 2 is 1 by 3. Correct? Cancel and cancel. So your answer is 4 by 3. 4 by 3 is nothing else but 1.3333 if you want to write it. I prefer writing it as 4 by 3. That is length of the queue. Length of the system is length of the queue plus the part that is being served. Length of the queue is 4 by 3. Part that is being served is 2 by 3, which becomes 3 common denominator. 4 plus 2 is 6 by 3. 6 by 3 is 2. And that is the length of the system. The length of the system is lambda into the weighting of the system. Length of the system is 2. Lambda is 60 weighting in the system. So weighting in the system is 2 by 60 R. I don't have place to write because I want to write WQ here. When I multiply this by 60 to change it to minutes, can I say 60 will get cancelled? So waiting in the system is 2 minutes. 2 by 60 R is 2 minutes. Length of the queue is lambda WQ. Length of the queue, which is 4 by 3, is lambda, which is 60 into WQ. This 60 will divide on the other side. WQ is 4 by 3 into 60 R. But when I multiply this by 60 to convert it to minutes, the 60 will cancel. And what will I get? I will get 4 by 3 minute. What is 4 by 3 minutes? Well, 4 by 3 minutes is 1.3333 minutes. But you know what 1.3333 minutes is? See, 0.3333 minutes is 60 into, is basically 20 seconds. So this is 1 minute and 20 seconds. So you are in the system for 2 minutes. In that 2 minutes, 1 minute 20 seconds you are in the queue. 1 minute 20 seconds you are in the queue. So the rest of the 40 seconds you are getting service. Let's come to what all are they expecting out of you. So expectation number 1, average queue length. Average queue length, which means LQ or length of the queue. The length of the queue is 4 by 3 or converted 1.3333. Let's check what their answer is. Well, here you have it. Sorry, I don't think I can scroll anymore. Let's do this. Let's do this way. Your length of the queue is 4 by 3 workers. Fantastic. So throw 4 by 3 workers in the queue. Question number 2 is average length of a non-empty queue. Let me skip that for the time being. Average number of workers in the system, including the workers being attended. So you are basically asking me the length of the system. The length of the system is LS and LS is 2. Is my answer? Let's see what their answer is. Well, their answer is length of the system is 2 workers. Fantastic. Let's go to the next. So I skipped one question. Let's go to the next question, which is question number 4. Mean waiting time of an arrival. See, very good question. They've not directly told you what to find. They've asked you the average waiting time of an arrival. Who are you talking about? Any person who arrives has to wait. Wait for what? Wait for service. Where will they wait for service? In queue. So you are basically asking me the waiting in the queue. The waiting time of a person in the queue, according to them, should be 3 by 4 minutes, which I have converted basically, and I have written it as 1 minute. No, this answer is wrong. Please make sure you change that. The answer is not 3 by 4, it's 4 by 3. I have copied it as and how from the material. That's wrong. It's not 3 by 4, it's 4 by 3. Please make that change. The answer is not 3 by 4, it's 4 by 3, which is what our answer is. You want waiting in the queue, no? Waiting in the queue is 4 by 3, not 3 by 4. So that's wrong. Anyway, coming back to the last question, and the last question is average waiting time of an arrival who waits. What is this? I'll tell you. Let's go back. Now, what do you mean by an average queue length? The LQ that we found, the length of the queue, what do you mean? Well, I'll give you an example. What I do is, I take, let's say, 10 students, and on different intervals, I send them to a ticketing counter at some station to take a ticket. And when they come back, I ask them 2 things. Number 1, or let's write it here. Number 1, how many how many people were there in the queue when you went there? So before you joined, how many people were there in the queue? And the second thing that I'm going to ask them to remember or record is, what was your waiting in the queue? Okay. So let's say we did this for 5 students. Student number 1 went. He said when I went, there were 4 people in the queue. And the total time I had to wait in the queue was 20 minutes. I said okay, till I got service. I said okay. Student number 2. He said when I went there, there were around 10 people in the queue and I got service in 30 minutes. Okay. Student number 3. Student number 3 said that when I went there, there was nobody in the queue. Okay. So did you wait in the queue? 1 minute. This is stupid. If there's nobody in the queue, why will I wait? I will directly go to the counter, no? So did he wait in the queue? No, there was no queue waiting. So queue waiting was 0 minutes. Student number 4, he said when I went there, there were 2 people and I got service in 10 minutes. And the last, student number 5, he said when I went there, there were 4 people in the queue and I got service in 40 minutes. I said okay, let's now find the average queue length and the average time my students had to wait in the queue. Okay, so average queue length will be 4 plus 4 is 8, 8 plus 2 is 10, 10 plus 10 is 20, 20 divided amongst 5 students is 4. This is my average queue length. So this is my length of the queue. And what was the waiting time that the students had to give in the queue? Average waiting is 20 plus 30 is 50. 50 plus 50 is 100. 100 minutes divided over 5 students is 100 divided over 5 is 20. 20 minutes. And this is how the study was made. On an average, there were always 4 people in the queue and the average waiting time in the queue is 20 minutes. Now one student will come up and say, sir, this is wrong. Why is this wrong? Arey sir, there was nobody in the queue when I went. So how are you considering this 0 as an entry? When you take an average, you are considering how many people in the queue. No, here there was nobody in the queue. Then why are you considering that as an entry? You should take a total which is 20 and not divided amongst 5 people, divided amongst 4. I will say, that's stupid. That is not how statistics works. Everybody gets divided. But then can I tell him that, okay, we are giving rise to a new condition. And the condition is, this is the length of a queue. But can I say in this, there were times when there was no queue. And if there was no queue, I should not consider that. Because I am trying to find length of a queue. If there was no queue, why will you consider that? And this gives rise to average length of a non-empty queue. What do you mean by non-empty? I am only going to consider those times where I actually had to stand in the queue. If I didn't have to stand in the queue or there was no queue that was found, if I directly went to the counter, then I'm not going to consider that entry. So if you ask me average length of a queue, I'm going to take a total of everything and divide it amongst all 5 people. But if you ask me non-empty queue, where I'm going to say there was once when the queue was empty, don't consider that. So if you are going to take an average, add the total, which is still going to be 20, but don't divide it amongst 5 people, divided only amongst 4. So that will be 20 by 4, which is 5 people. So in general, 0 queue will also be considered a queue, and I will consider that as a reading and take an average and divide it amongst that 0 also. But when you ask me non-empty queue, that empty queue I will not consider. Similarly, sir, average waiting time is 20 minutes. He's like, sir, 1 minute. I did wait. I didn't wait at all. Why are you considering my time? Arey, but I have to know. That is how statistics works. If somebody gets 0 marks or somebody gets 50 marks, we are still going to consider both as a data value and take an average and divide it amongst both. But then because you are posing this problem now, let me introduce you to another concept. And that concept is we are going to find the waiting time of an arrival. Correct? This is waiting time of an arrival. We are going to find waiting time of an arrival who waits. What do you mean by waiting time of an arrival who waits? Well, there is one person who didn't wait. I'm not going to consider it. My average is going to be divided amongst the 4 people. So it's 100 divided by 4, which is 25 minutes and not 20 minutes. And these were the last 2 concepts that I told you. We are going to do 2 more formulas, and these are it. And that is ln. What is ln? ln is the length of a non-empty queue. Every queue, there is a chance that there was a point where there was nobody in the queue. The person who came in directly went in for service. If you don't want to consider those points, then the formula is ln is 1 upon 1 minus rho. And if you want to ask waiting time of a person who waits, so non-waitings will not be considered, and that is Wn, and that is given by ln is mu Wn. Waiting time of an arrival who waits, length of a non-empty queue. Go back to the first page where we wrote down all the formulas on one page. It is now that I will definitely not find that page. No, I have found that page. And here we will write down 2 new things. And one is ln, and that is again length, or basically number of people of a non-empty queue. And remember, this length will be greater than your length for a simple reason that your length is considering 0 number of people in the queue also. This is not. So this will be more than this. And ln is given by 1 upon 1 minus rho. Then we have ln is lambda Wn, where Wn is average waiting time of an arrival who waits. There might be people who don't wait, who directly go for service because there is nobody in the queue. Those people I am not going to consider. So ln Wn, that's it. These are 6, 7, 8 formulas. If you have these in place, gold. Let's go back to the question. Now I will have conveniently lost that. No, I have that question. Fantastic. So this was the question given to us. Lambda was 60, mu was 90. We found rho, which is 2 by 3. We found LQ, which is 4 by 3. We found LS, which is 1.33. Their answer is wrong. 3 by 4 is not the answer. 4 by 3 is the answer. Anyway, LS is 2 minutes, length of the system, and WS, which is waiting in the system, is 2 minutes, and waiting in the queue is 1.333 minutes. We come to the last 2 things that they have asked us is length of a non-empty queue is 1 upon 1 minus rho. Rho is 2 by 3, so it is 1 upon 1 minus 2 by 3. Take an LCM, 3 ones are 3, minus 2 is 1, 1 upon 1 by 3, which is 3. And lastly, waiting of a person who waits. Non-waiting don't consider. So that will be ln is mu Wn. 3 is mu, which is 90 Wn, or Wn is 3 upon 90, and this is in hours. You can divide it, but you will get a recurring decimal. I don't want to. I'll convert this to minutes. So Wn is 3 by 90 into 60 minutes. Sorry, 3 into 60 upon 90 is going to be 3 into 60 divided by 90. and the answer is 2. So 2 minutes. So length of a non-empty queue is 3 and waiting of a person who waits is 2. Let's go back and check what their answer is. So length of a non-empty queue is 3 workers. Fantastic. Which is the same answer that we also got. Correct. And lastly, average waiting time of an arrival who waits is 2 minutes. That's it. Concept wise, queuing theory is done. All concepts are covered. Now the next, this was question number 4 if I'm correct. No, this was the last question. Question number 6. The next question that I want to do, which is a slightly different question, because it's not different in that way. There is costing involved. So you have to do everything and then you have to do a costing bit. So let's jump on to the question then. Question number 5. As a tool service center, the arrival rate is 2 per hour. So again, it's a tool service center. I don't need to tell you what a tool service center is. At a tool service center, arrival rate is 2 per hour. So 2 people come in per hour. And a potential of 3 per hour simple queuing and service potential is 3 per hour simple queuing conditions exist. So arrival rate is 2 per hour and service rate is 3 per hour. Fantastic. 2 by 3 is the value of my rho. What do you want from me? The hourly wage paid to the attendant at the service center is 1.50 per hour. And the hourly cost of a machinist away from his work is 4. Calculate the number of machinists being served or waiting to be served at any given point. The average time a machinist spends, or let me do one thing. Why do all of this? Can't I just directly find everything and then give them what they want? Because anyway, I'm going to end up finding everything. Fine, let's do that then. So the question says, as a tool service center, the arrival rate is 2 per hour. Arrival rate is lambda. So lambda is 2. And the service potential is 3 per hour. So mu is 3. Immediately rho is 2 by 3. Done. Now before you ask me anything, let me give you everything as a now. Length of the queue is rho square upon 1 minus rho. Now you can convert this and do it. I don't want to. I'm sticking to substituting as and how it is in fractions. So 2 by 3 square divided by 1 minus 2 by 3, which is 2 by 3 into 2 by 3 divided by LCM. 3 ones are 3, minus 2 is 1 by 3. 1 3 and 1 3 cancels. You are left with 4 by 3. And we know that 4 by 3 is 1.3333. It's up to you how you want to keep it. This is the length of the queue. Length of the system is length of the queue plus rho. Length of the queue is 4 by 3. Length of the rho is 2 by 3. Again, 4 plus 2 is 6 divided by 3 is 2. So there are 2 people in the system, out of which 1.33333 are in the queue. And the remaining, which is I think 6.67777 is going to be in the at the service center getting served, because 2 by 3 will be 0.66666 if I'm right. 2 divided by 3. Perfect. 0.6666. So 0.67 is getting served. 1.333 is in the queue. So total in the system are 2 people. Length of the system is lambda ws. Length of the system is 2. Lambda is also 2 waiting in the system. So waiting in the system is 2 by 2, which is 1 hour. Length of the queue is lambda wq. Length of the queue is 4 by 3. Lambda is 2 into wq, or 2 comes down. Wq is 4 by 3 into 2, which is, so this is an hour, which is 4 by 3 into 2 into 60 minutes, which is, this is 6. So 6 cancels, 40. So I think 40 minutes. Yes. Correct? Common sense, no? 1 hour the person spends in the system, out of which 40 minutes he is spending in the queue, which means 20 minutes for service. Obviously, didn't they just tell you that I can serve 3 people in an hour? So per person, 60 divided by 3 is 20 minutes, no? So to serve one person, it is taking 20 minutes. Perfect. 40 minutes in the queue, 20 minutes getting served is 60 minutes in the system. Done. Let's answer whatever they have for now. So what do I have? I have length of the queue is 4 by 3, length of the system is 2 by 3, waiting in the system is 1 hour, and waiting in the queue is 40 minutes. Let's see what they are asking. So question number 1. The average number of machinists being served or waiting to be served. So being served or waiting to be served, which means number of people in the system. And number of people in the system is 2, according to me. Is that their answer? Yes. If you notice, they have written here LS is 2. Next, the average time a machinist spends waiting for service. Where does someone wait for service? In the queue. So you are basically asking waiting in the queue. Waiting in the queue is, like I told you, waiting in the queue is, if you write it in decimals, if you write it in hours, it is going to be a decimal. So it's going to be basically 4 by 6. But if you write it in minutes, it's going to be 40 minutes. Anyhow that you want to write is okay. Number 3, the total cost of operating the system in an 8-hour day. Okay, now you are asking me costing. Let me understand the costing. The hourly wage paid to the attendant. So there is an attendant who is attending to these people. You are paying him at a rate of 1.4 rupees. And hourly cost of a machinist away from work. What do you mean by away from work? See, if a machinist, which is basically my worker, wants something and he comes to the tool shed, isn't he wasting time? Or basically, am I going to deduct his salary for that? I can't. So I have to pay him for that. So if he is waiting in the tool shed, I am still paying him salary for that. So the more time he waits in the tool shed, the more time I have to pay him for extra, or I have to pay him for no reason. So can I say, when you ask me the total cost of operating in an 8-hour day, and you have given me 2 costs. 1, the cost of the person who is attending to everyone, and the cost of the machinist being away from his job. These are the 2 people whose costing I have to consider. And what are the costings? The cost of attendant is rupees 1.5. I am paying him 1.5 rupee per hour. And cost of machinist away from work. Machinist away from work is how many? 2 per hour. Okay, let me start doing the costing for you then with whatever data I have. Let's do something called as an hourly cost. Okay. Hourly cost of attendant is, well, attendant's hourly cost is 1.5 rupees. Fantastic. Plus the hourly cost of a machinist away from work. Okay. So understand what I am saying properly. Whenever I go to the tool shed, on an average, there is always and always 2 people in that system. So, 2 people are wasting time there. Okay, I'll repeat this. Whenever I go to the tool shed, there are 2 workers that are stuck in the system. These 2 workers that are stuck in the system are wasting time there. But how much time are they wasting? Well, on an average, 1 person is wasting 1 hour. How many people are stuck there? 2 people. Then 2 people together, every hour will waste 2 hours. Understand what I'm saying? Every person is stuck for 1 hour. But at any given time, how many people are stuck? 2 people. So 2 people stuck for 1 hour each is a total of 2 hours. So every hour I am losing 2 hours worth of machinists. So machinists away from work is the number of machinists stuck in the system into the average time that they waste in that system into the cost that I have to pay them, which is 2 rupees. So every hour I waste 2 machinists wasting 1 hour each for 2 rupees is a total of 4 rupees. So the total cost that I am wasting per hour is 1.5 plus 4 rupees, which is a total of 5.5 rupees. 5.5 rupees wasted per hour. So in an 8-hour day, for an 8-hour day, the cost is 5.5 into 8. And what is 5.5 into 8? 5.5 into 8 is going to be 44 rupees. So on a given day, I have wasted 44 rupees because every hour, no matter when you go, there will be 2 people stuck there and each person will be stuck for an average of 1 hour. So if each person is stuck for an average of 1 hour, which means that I'm wasting 2 hours every hour. 2 hours wasted every hour is 4 rupees wasted every hour. The 4 rupees that the machinists are wasting and the 1.5 rupees that the attendant is what I'm giving him is a total of 5.5 rupees per hour. 5.5 rupees per hour for an 8-hour day is going to be a total of 44 rupees. Let's quickly check their part of the solution. Their part of the solution is number 3. Average time in the system is 1 hour. Average number of machinists is 2. Cost of 2 machinists being away from work. Now they haven't written this. Cost of 2 machinists being away from work for 1 hour every time is 8 rupees. Because 4 into 2 is 8. Is that right? 1 minute. Have I made a mistake? Oh, I'm so sorry. I'm extremely sorry. I read that wrong. I'm paying the service guy 1.5 rupees and the machinist 4 rupees. I'm so sorry. So the answer will be into 4 rupees that I pay the machinist. So 4 twos are 8 rupees. Sorry about that. 8 rupees plus the 1.5. 8 plus 1.5 is rupees 9.5 per hour. 9.5 for 1 hour. So over 8 hours, 76 rupees. I'm sorry, extremely. So in 1 day, I have wasted 76 rupees. Correct? That is their answer, which is when I realized I have copied something wrong. Anyway, here, so their answer is 76 rupees. Correct? This is the second part to the question. The second part to the question says that the cost of the system if, so now they're changing something. There were 2 attendants working together. Fantastic. See, now when you told me that 1 attendant is attending, 1 attendant can attend 3 people. So if you put 2 attendants, there will be 6 people worth service. If there is 6 people worth service, there will be lesser waiting in the system. And if there is lesser waiting in the system, I might end up saving money on the workers. So let's continue and see what they are trying to say. What they are saying is the cost of the system if there are 2 attendants working together as a team Each paid 1.5. Perfect. If one person is getting paid 1.5, then each two people will get paid 3 rupees. So there the cost will be high. But it might happen that the waiting might reduce. So then the waiting cost will be less per hour, and each able to serve 2 per hour. Oh, they've changed something. See, initially we were able to serve 3 per hour. They changed that and they made it. Now these two attendants cannot serve 3 people each. So they can't serve 6 people. They can only serve 2 people per hour on an average. 2 people per hour with 2 people is going to be 4 people. So that is what changes. So if that changes, then a lot of things will change. And that is mainly how many people stuck in the system and for how long will change. So let's start the costing again with the changed question. And the costing will be, I'm going to say lambda now is still, what is the arrival pattern? The arrival pattern doesn't change, it's still 2. Mu has now been changed from 3 to 2, but the number of servers has been made 2. So 2 people but can't serve 3 per person, they can serve 2. Now you'll ask, sir, why? If it's the same room, shouldn't they serve double? See, what happens is, suppose there's a register and there's only one register. So both of them are giving the worker tools, but there is only one register. So when they are making a note, one has to wait for the other. So you can directly serve double the number of people. You can serve slightly lesser. So technically you should have been able to serve 6 people, but we are only serving 4 people. But that's still more than what I was serving initially. Initially I was serving 3. Now I will be serving 4. So I will say rho is lambda upon mu into m, which is 2 into 2 into 2, which is 4, which is basically 0.5. So rho is 0.5. Length of the queue is rho square upon 1 minus rho, which is 0.5 square upon 1 minus 0.5, which is 0.5 square upon 0.5, because 1 minus half is half. 1.5 cancels, the answer is 0.5. Length of the queue is half. So if you notice, the length of the queue has reduced. Initially, the length of the queue was here 4 by 3, which is 1.3333. Now the length of the queue has only become 0.5, which means at any given point, there is only half a man in the queue. How many in the system stuck? That is what is more important to me. Length of the system is length of the queue plus the part that is getting served. Well, length of the queue is 0.5. The part that is getting served is also 0.5, which means 1. If you notice, the number of people stuck in the queue is reduced. Initially, there used to be 2 people stuck in the system. Now, there is only 1 person stuck in the system. Let me find out for how long is this 1 person stuck. For that, I need WS. LS is lambda WS. So 1 is, what is lambda? Lambda is 2 WS, or WS is 1 by 2 R, or WS is 0.5 R. So if you now notice, whenever I go, there is 1 person in the system, but that 1 person is only stuck in the system for half an hour. Initially, whenever I went, there were 2 people stuck in the system and every person was stuck for 1 hour. Now, there is only 1 person stuck in the system for half an hour. Let's come to daily cost. Attendant. Now attendant will be 1.50 per hour, but there are 2 attendants now, which means I am paying 3 per hour for attendant. And machinist is how many people stuck in the system, for how long are they stuck on an average, and what is their cost, which is 4 rupees. Length of the system is 1. This 1 person is only stuck for half an hour. I am paying them at the rate of 4 per hour. So I only have to pay half the money. which is 2 rupees, because I'm only wasting half an hour. If 1 hour I pay 4 rupees, then half an hour I have to pay 2 rupees. The total cost per hour is going to be 3 plus 2 per hour, which is rupees 5 per hour. Now if it's 5 per hour, then for an 8-hour day, what is it going to be? It is going to be 5 into 8, which is 40 rupees per day. What did they ask me to do? Let's go back to the question. The question says the cost of the system if there are 2 attendants working together as a team paid 1.50 per hour and each able to serve 2 people. So that's it. That's all that is asked. Okay. Let's look at their solution. Here, if you notice, their solution is also 40 rupees, which means their solution and our solution is the same. I will quickly do a recap and then we'll wind this up. There is a tool store where there is a person who is attending to machinists who come there for tools. Okay. What is happening is there are 2 people that come every hour for service and the tool attendant can attend 3 people in an hour. So the row is 2 by 3, length of the queue, length of the system, waiting of the system, waiting in the queue. Now when you ask me to calculate costs, every hour what am I paying for? I am paying for 2 things. Number 1, I am paying the attendant every hour. And number 2, on an hourly basis, I am paying the machinist, but he is being away from work. And that is the cost I have to calculate. How much cost am I incurring for him away from work? So they have given me that is 4 rupees per hour away from work. Okay. So the machinist is 1.5 rupees per hour. That is fixed. What about the worker? Well, every time I go to the tool shed, I see 2 people stuck in that tool shed. 2 machinists stuck in the tool shed for service. These 2 on an average are stuck for 1 hour, which means every machinist is stuck for 1 hour. If every machinist is stuck for 1 hour on an average, which means 2 people together every hour are wasting 2 hours of mine. If they are wasting 2 hours of mine, I am paying them 4 rupees per hour, which means that I am paying them 8 rupees per hour. That 8 rupees per hour plus the 1.5 rupees is 9.5 rupees. 9.5 rupees per hour is a total of 76 rupees on an 8-hour basis or a per day basis. After that, what they said is, I am increasing the number of tool attendants. Fantastic. So they are putting 2 servers, 2 tool attendants. Now initially every tool attendant could attend 3 people. So 2 should be able to attend 3 plus 3 is 6. But they are saying no, it doesn't work that way. When I add 1 more tool attendant, the total number of attendants doesn't become double. I can't attend 6 people. I can now attend 2 people per attendant. So what I say is that you've increased the server and put 1 more server, so M is 2. And the number of people being served now is 2. Even then 2 into 2, 4 people per hour, which is still good. My row will change, my LQ will change, my LS will change, my WS will change. And obviously if you put more number of servers, the waitings will reduce, the length of the queue will reduce. So now I find the length of the system and I find on an average how long does a person has to wait in the system. And I will say daily cost is attendant costs me 1.5 per attendant, but there are 2, so into 2. And at every given time there is 1 person stuck in the system for half an hour on an average. I am paying them 4 rupees, so every hour I am wasting only 2 rupees. That 2 rupees plus the 3 rupees is 5 rupees. 5 rupees on an hourly basis. So on a daily basis, 5 into 8, which is 40 rupees per day. That's the answer. Sometimes what they say is calculate the daily savings. So 40 rupees is the reduced rate. And there I was paying 76 rupees. 76 minus 40 is what I will save. How much will I save? 36 rupees is what I will save every day. That's your answer. That is the last question in the sheet. That leaves us with one last question, and this question is different. Like I told you, your module, the person who designed this, I tell in every batch, whenever you clear and you become a CMA, the first thing you will do is you will go to the institute, which is in Kolkata, go there and ask them who has printed or designed the OM syllabus. The moment they introduce you to that person, grab hold of that person, don't leave them, make me a call and tell me, and I will be there with the next flight as soon as I can, and we will sit and talk to that person over coffee as to who, किसने इतना दर्द दिया था आपको कि आपने इतना घटिया syllabus design किया. Anyway, it could have been done in a very beautiful way, but no. Fine, we come to the last question of queuing theory. With this, queuing theory will come to an end. What is different in this question? Let me read the question. Wanda's car wash and dry. So there's a car wash and dry where they wash your car, they clean it for you, they dry it for you and give it to you. Is an automatic 5-minute operation. What do you mean by automatic 5-minute operation? The service is fixed. The service is not random. This can serve one car in 5 minutes. One car in 5 minutes is 12 cars an hour. And 12 cars an hour is never going to change. It's a fixed operation. And that's the problem. This is not an MMC infinity model, because in an MMC infinity model, arrival is random, service is random, service is not random, service is deterministic, service is fixed. They didn't say takes an average of 5 minutes. No. If they would have said average of 5 minutes, which means yes, some cars take more than 5, less than 5, on an average 5, then I could say that okay, this is random and it is probabilistic or it is exponentially distributed. If they are saying that it is automatic 5-minute operation, they do not mention that automatic average of 5-minute operation, then this is a fixed service question with a single bay. What do you mean by a single bay? There is just one server or one service center. There is just one bay that will wash cars. On a typical Saturday morning, cars arrive at a mean rate of 8 per hour. Do you understand that arrival is random? Because they've said average of 8 per hour. They didn't say exactly 8 hours come every day. On an average, 8 hours come every hour. With arrivals tending Poisson distribution. See, they told you arrival is Poisson distributed. Service is not exponentially distributed. And that's the problem with the question. And when you come across such a question, or when you come across a model that is not MMC infinity, I told you there could be multiple models. There could be models where arrival is fixed, service is random. Like the doctor I told you. When you go to a doctor with an appointment, everybody is given like a 20-minute duration appointment. So 8, next 8:20, next 8:40, next 9, 9:20, 9:40, 10 and so on. But then the service that the time will take, it's not compulsory that if a patient comes in at 8:20, he or she will get to go in at 8:20. No. There might be a patient inside, or it might happen that the previous patient was done 5 minutes ago. So then you can directly enter. So there, arrival is fixed, service is random. Your arrival is random, service is fixed. What do you do in such a question? Well, just one small thing changes, everything else remains the same. So the problem or the change in this question is that it is not an M1 infinity question. It is an MD1 infinity question, where arrival is random, service is fixed, or service is deterministic. And if service is deterministic, you can't use the same formulas. Well, let's at least find lambda and mu. So lambda, which is arrival, arrive at the rate of 8 per hour. Fantastic. Service, which is mu, it's a 5-minute operation. Fine. Then 5 minutes I service one vehicle. Correct. So in 60 minutes I will service mu vehicles. So the answer is mu is 12 per hour. So rho is lambda upon mu. That also doesn't change, which is 8 upon 12. You can cancel, but it will become a recurring decimal. I don't want to. 4 2s are 8, 4 3s are 12. 2 by 3 is what I'm keeping it at. And now things change. And the thing that changes is one very small thing, everything remains the same. What is your usual length of Q? Well, my usual length of Q is rho square upon 1 minus rho. Perfect. Now, remember I told you, now because both are random, there is randomness in the environment. That is why the waiting times are more and the length of the queue is long. If everything is very fixed, the more determined you get, the better you get at estimating values, the queue will become that much smaller and people will have to wait lesser. And that is why in this question, because the service is deterministic or fixed, there is no random pattern in the service, the length of the queue reduces to exactly half of the normal, which is half of MM1 infinity infinity model. In the MD1 infinity infinity model, the length of the queue becomes exactly half. Everything else remains the same. Like because see, LS depends on LQ. Correct? WS depends on LS, which depends on LQ. And WQ depends on LQ. So once LQ is defined, everything else can automatically change. So you don't have to remember like 50 other formulas. So the answer is the length of the queue in this case will be 2 by 3 square divided by 1 minus 2 by 3 into half. So the length of the queue will be half into 2 by 3 into 2 by 3 divided by 3 ones are 3 minus 2 is 1 by 3. Correct? The 3 and 3 cancels. What are you left with? Well, I'm left with 2 into 2, which is 4 by 3. So half of 4 by 3, which is again 2 by 3, is the length of the queue. If you want to convert it, it will be 0.666, 0.67. What will be the length of the system? Well, that will remain the same. It is the length of the queue plus the part that is getting served. Length of the queue is 2 by 3. Length of the value of rho is also 2 by 3, which becomes 4 by 3, which is 1.333. Waiting length of the system is lambda ws. Length of the system is 4 by 3. Lambda is 8 ws. 8 goes down. So this will become ws is 4 upon 3 into 8 hours, which is 4 upon 3 into 8 into 60 minutes, which will become 4 into 60 divided by 3 divided by 4 into 60 divided by 3 divided by 8. The answer is 10. So 10 minutes is the waiting in the system. Now you tell me, if the waiting in the system is 10 minutes, you are in the system for 10 minutes, out of which 5 minutes you are getting service, then what should be the waiting in the queue? 5 minutes. LQ is lambda WQ. LQ is 2 by 3. Lambda is 8 WQ. So WQ is 2 by 3 into 8 R. Correct? If I have to convert that to minutes, I have to multiply by 60. So it becomes 2 by 3 into 8 into 60 minutes. So that is 60 into 2 divided by 8 divided by 3. The answer is 5. And I told you, if you are 10 minutes in the system, out of which you are spending 5 minutes in service, then you are 5 minutes in the queue. So length we are waiting in the queue is 5 minutes. That's it. Let's check what they were asking. I have found everything. Sometimes check what they are asking. If it's just one thing, then find that only. I have found everything. Yes, perfect. What is the average number of cars in line? In line, so length of the queue. Length of the queue is LQ 0.66666, which is 0.67. The average time a car spends in line and service. 5 minutes in line, 5 minutes in service, 10 minutes. That each eat. That's it. With this, the chapter queuing theory comes to a sweet end. Now, again, like we always do, we check question papers, what has been asked for how many times and how many marks. Let's quickly go to question papers. Let's try to fit this into us. So, chapter number 7 if I'm right, and this is, what are we doing? Queuing theory. Correct? Let's start with question papers. What do you need? Importantly, this. If you have this, gold. Row LQ, LS, WS, WQ, probability of 0 people, probability of n people, average length of a non-empty queue, and waiting time of a person who waits. Let's begin. The first question paper, which is the June 17, skip past the objectives. So 2A no, 2B no, 3A no, 3B, again the marking is gone, was done under time and motion. Then simulation, so no. Question 4B was done under productivity. 5A no, 5B no. So the first question paper not asked. Okay, let me go to the second. 2A no, 2B done, 3A no, 3B yes. And imagine 9 marks, 3 questions for 9 marks. Workers come to a tool store room to inquire about special tools required for them by them for accomplishing a particular project assigned to them. The average time between 2 arrivals is 60 seconds. Then can I say, if the average time between 2 arrivals is 60 seconds, then every 1 minute one person comes, and the average service time of the attendant is 48 seconds, which means to attend one person, it takes 48 seconds. Now that I don't understand. Convert that for me and make it into what happens on an hourly basis. What do you want? Average queue length, average length of non-empty queue, and average number of workers in the system, including the workers being attended. So you basically want all L's. You want LQ, LS and LN. Let me quickly solve whatever I can for you, and please make sure that you create this solution right behind where you have written this itself, so that you know it's better for you to refer to things whenever you want to or you have to. So that first part, 60 seconds one person arrives, which means 1 minute, which means lambda is 60. Every 1 minute one person arrives. In 60 minutes 60 person will arrive. Now the other is one served in 48 seconds. I want to know how many are served in 1 hour. 1 hour is 3600 seconds. So mu is 3600 upon 48. What is 3600 upon 48? Well, 3600 divided by 48 is 75. So you can attend to 75 people. So rho, which is lambda upon mu, is 60 by 75. 75 again has a 3 in it. 60 also has a 3 in it. So this just might work out. 60 divided by 75 is 0.8. Perfect. 0.8. So I am going to say length of the queue is rho square upon 1 minus rho, which is 0.8 square upon 1 minus 0.8, which is 0.8 into 0.8 upon 0.2. 0.8 square upon 0.2, 0.8 square it divided by 0.2, and the answer is 3.2. So length of the queue is 3.2. Length of the system is length of the queue plus the part being served. So 3.2 plus 0.8, which is 4. And lastly, I have average length of a non-empty queue, which is 1 upon 1 minus rho, which is 1 upon 1 minus 0.8, which is 1 upon 0.2, which is basically 5. So technically there are 4 people in the system, but then if you are considering those times where there is nobody and the person directly goes for service, then there are 5 people in the non-empty queue. Is that it? Yes. So that is one question for 9 marks. What all was asked? What was asked was LS, LQ, LN. Let me make a note of that. So one question, 9 marks. LS, LQ, LN was asked. Fine. Let's continue. Four A is done, 4B is done, 5A no, 5B no. Let's go to the next question paper, which is the June 18 question paper. Yes, so 2A no, 2B no, 3A no, 3B no, 4A no, 4B yes. At a tool service center, the arrival is 3 per hour and the service is 4 per hour. Simple queuing conditions exist. The hourly wage paid to the attendant of the service center is 2 per hour and the hourly cost of the machinist away from his work is 5 rupees. Calculate the average number of machinists being served or waiting to be served at any given time, the average time a machinist spends waiting in service, the total cost for an 8-hour day, and the cost of the system if there were 2 attendants working together, each as a team paid 2 per hour, each able to serve 3 people. Here he was able to serve 4 people, but here 3 people and doubles. Exactly the same question. I'm not going to do it. The question is asked for 8 marks. This is so stupid. So much asked and only for 8 marks. There hardly anything asked but for 9 marks. Anyway, let me make a note of it. I'm not doing the question. I want you to do it. And that is one question for 8 marks. Costs are involved. So there was costing that was asked. Let's keep moving to the next question paper, and that should be the December 18. Yes, December 18 question paper. In the December 18 paper, skip past the objectives, descriptive. 2A no, 2B done, 3AB no, 4A no is transportation, 4B no is simulation, 5A is project management, 5B is no, maintenance management. No question asked in that year. Let's go to the next question paper, which is the June 19 paper. Correct? Yes, the June 19 paper. Skip past the objective, descriptive. 2A no, 2B done, 3AB no, 4A is a assignment problem question, 4B is a, oh yes, 4B is a queuing theory question. A taxi operator is planning to open a computerized ticket counter in a center of the city, staffed by one ticketing agent. This is like that airline question. It is estimated that requests for the ticket and information will average at 18 per hour. 18 is the arrival and requests will be Poisson distributed. Service time is assumed to be exponentially distributed and the service is on an average of 2.5 minutes per request. So see, it takes 2.5 minutes for me to serve one person. I have to find out how many I can serve in 60 minutes. 60 divided by 2.5 is 24. So arrival is 18, service is 24. What are you asking? System utilization. System utilization is nothing else but lambda upon mu, which is rho, which is 18 upon 24. You know what 18 divided by 24 is? 75%. Percentage of time the server is idle. Well, if 75% it is working, 25% time it is idle. Expected number of customers waiting to be served. Waiting to be served. Where do they serve? In the queue. So they are asking you the length of the queue. An average time a customer will spend in the system. Then they are asking you waiting time in the system. So this is basically rho. This is 1 minus rho. This is waiting to be served is LQ, and this is waiting in the system time, which is WS. Second question is asked for 2 into 4, which is 8 marks again. So good question, asked for 8 marks. I want you to do it. So one question, 8 marks. Let's come to the last paper, and that is December 19. Skip past the objective, descriptive. 2AB, no. 3AB,